Cool. This stuff out of here. There we go. Okay, we're back. Hopefully Halloween weekend was just what it needed to be. Either spooky, scary, relaxing, silly, I don't know. But we're back. We jumped into, so last Wednesday we did this first, problem 2 for chapter 4, problem 2. And now we can go right into like 4.6, looking at this moving frame, so a moving frame of reference, and then the main thing here is looking at like conservation of angular momentum in different frames. Like, what does it mean? How do we define it? And what does that do for us? And this kind of thing. So there's a bunch of steps to kind of go through, but from bird's eye point of view, really what we're doing is defining our, like, what is the motion? So we're going through the kinematics, and once we know that, the kinematics are what define like momentum and angular momentum, and then looking at like what are the forces involved. So what kind of torque is, what kind of moment is there? Bless you. And then comparing a moving frame to our fixed, like unmoving frame. And like the diagram is nice because it's a good like engineering kind of thing. But what this would look like in, you would have like some kind of like table on rollers. And it gets, as it gets pushed, this thing is attached to a spring. It could be a spring or a pendulum. Like the same thing would happen. Or a ball like in a bowl. Like if you were driving down the road with like a circular kind of bowl, you have like a linear kind of spring problem. So it'll start moving in this ellipse in a circle as it like starts moving, as you like shove it and start going. So that's what we're trying to figure out. It's like what happened, like how do we describe that, what's constant, and these kind of things. Usually there's a little bit of struggling with this one, so we'll go through it kind of step by step. So we want coordinates of our own choice. What is position? What is velocity in the moving frame? So we have this like little prime here. So what is position? How do we describe position? And how do we describe velocity in that O prime frame? What are those? How do we describe that? And just give it a shot, see what you think. What do you want to do with that? just like angle. Okay. You use cylindrical? Yeah. That would work.
What's the frame?
There's like O, which is some global fix. It's not moving. And then O prime, and it's moving at a constant speed.
Oh, I see. Okay.
What did you write for the position? How do you describe that? Okay.
Yeah.
What's the position look like per cylindrical coordinates?
Oh, I see that.
Okay, yeah. So it's just like describing it. Yeah, we could have like some kind of design. This one, right? So like
I'm just trying to better understand what is it that we're modeling?
it's rotating.
Or is it just like?
Oh, it's like what's happening?
Yeah.
That means it's a mass like on springs and on a table that it's like going
Oh, okay, so the spring.
moving around.
No way, it's okay.
It's as it moves around. Ideally, it would just want to move around in a circle.
Yeah.
So instead, the springs are right, so now it moves a little slower. And then because it slows down, it's less centrifugal. Back and down moves faster. And more centrifugal acceleration to slow down. So you end up doing it less.
Yeah.
And the whole table is like moving pretty much.
Yeah.
Yeah.
Yeah, I think that forward makes the most sense. I think it's going.
Like this would be the same model as like Earth and the Moon.
Yeah.
Going around Europe. Yeah. It's just it's perfect gravity, so it's not going to your spring. So it's okay.
Yeah. Totally. I was going to send it But I thought you'd appreciate my Halloween costume.
Oh, nice.
It was my girlfriend. I went to school in Stacy.
Oh, awesome.
Yeah.
That's great.
And then she did like a little bit of love back for the scene where she followed. really good reference.
Oh, no. Oh, that's like a heartbreaking
Yeah,
story.
I know.
That divided a lot of the Spider-Man fans.
I don't know, she was really keen on doing that, but she wanted people to get the records.
Yeah. All right, this is usually where people are stuck. Did anyone have anything like a first step? Dynamics is weird because a lot of times you're writing down stuff that you do not know, and that's what we're trying to do here. Like, we don't know where this thing is, we don't know where it's going, so we're just trying to define, like, if we had a variable that we did know, what is that variable? That's really what we're trying to do. So, so when we're saying like we need coordinates of our own choice, we're trying to say, do we want to use, right now we have this reference frame of like B1 and B2. Do we want to call this like X and Y? Like its position is an X and it's a Y? A no? Why not? No XY?
Well, I don't know about it with respect to O, but at least with respect to O prime, the fact that it's not fixed, it's polar there, because it can swing, and that's theta, and then it's
yeah, there's like something circular about it, right? Like it's moving in some kind of circular motion. The spring is always along like that radial coordinate, like it feels like position should be coordinate of choice. So rather than like coordinate of choice, we could say polar coordinates. Nope, didn't mean to do that. R of P / O prime. So what is position in a polar coordinate system? Like, what do you need to know? Yeah.
Theta and the radius.
Theta and radius, yeah. So if we know theta, we know radius, then we know where it is. How do we write that in terms of like value, like unit vector and value? Is there like a theta times a unit vector or an r times a unit vector? What's our coordinate system now? R theta? Yeah. So do we just write it as like r theta?
like the
R plus theta? Something r and theta, yep.
We have the equation referring to position for the R times R hat, and the position reflects the change in theta times theta hat.
Yeah, so R, like ER, something like this, like the E hat. And so this is it. That's all you need to describe position. What is the radius? What is the unit vector describing where it is? Yeah. And that unit vector points out along here, kind of like this. So if we need to know where that is, like what is the unit vector, what is the direction, we can always calculate it because it's cosine theta along that B1 plus sine theta along that B2. So we have a magnitude 1 vector that we can describe in terms of only theta. Theta is the only thing that changes that unit vector. Yeah, so at least that's our first step. What is position? It's radius times a unit vector, and that's, we don't know what the unit vector is, we don't know what radius is. And again, if you're struggling with that, of like, why am I even writing this? That's okay. Welcome to dynamics. It's a dynamic class. Things keep changing, and we're just trying to like nail down what can we keep constant.
What is the straight line over the R you expect to go prime?
Oh, what's that like little? It's a top hat. Say like I'm a fancy vector, and that's it. Because I can't normally in a textbook bold, but I can't. My handwriting's not very good to say like this is my bold handwriting and this is my regular, so I put a little like line hat over it. Then I use caret hats to say unit vector. So vector is kind of line, and then caret is unit vector, just direction. At least that's how I designate it. Other people, I'm trying to think of what else I've seen for handwritten. Usually lines, I think. There might be other ways. I like the lines and hats. What is velocity? Yeah. It's a derivative, right? It's going to be our change. We could take a derivative of it, right? What's the derivative of r? Yeah, dr dt. Like, so we have an r dot in that er. And then what about er? Is that one changing? Or is it a constant unit vector? It is pivoting, right? So it's definitely changing direction. So there's got to be a derivative. Yeah.
If we define ER as cosine theta v1 sine theta v2, we can take the derivative of that as well.
Yeah. So we can take derivative of that, and what we end up with is r. That theta dot looks weird. E theta, 90 degrees to ER. Like E theta is pointing 90 degrees. And that's what we need for a coordinate, at least 2 dimensions. We need 2 unit vectors that are 90 degrees to each other. So we have an ER, we have an E theta, and that's. And in this case, this is the definition for like what is velocity in a cylindrical coordinate system. So we could have just looked up like how do I describe position, velocity in cylindrical coordinates, and gives us the same answer. Yeah.
Why wouldn't we be taking the derivative for cosine theta v1 sine theta v2 function?
You want to do it?
Would we to, I'm just wondering why.
Let's write it out. So derivative of cosine theta is going to be a theta dot sine theta. Is it positive or negative? Negative. B1 is a constant, so there's no derivative of B1. And then sine theta is going to be a theta dot times that cosine theta, B2. So a negative sine, so that theta dot, I can pull it out. So now I have a negative sine theta and a positive cosine. So negative sine along that B1, which is, all right, so let's do this. So if that's my theta, if I take that sine theta and flip it over here and call it negative sine theta, take this cosine theta, put it up here, really that derivative just rotated it by 90 degrees. That one's kind of weird, but it is pretty cool. You can d theta of sine and cosine just rotates it by 90 degrees. And it happens to do that because sine and cosine are 90 degree phase changes from each other. 90 degrees. All right, I'm going to redraw. We call that VO. Yeah, VO. All right, next question for part B is we defined position, velocity in the moving frame. So like as if we're sitting in the car watching this thing move, what's happening? Now, if we're an observer watching the car go by, what is position velocity to the fixed observer watching this thing in motion? How do we describe that? We know how fast, this is like a fixed value, call it 15 miles an hour. Like it's a fixed value. So we know it's moving at a constant speed. We know what the constant speed is. So how do we describe position and velocity now? Oh, nice. Thanks, Jimmy. And let's scroll up so we still have our previous work. Yeah, you can mix and match coordinate systems, and that's okay. Yeah, for that thing, so. mix and match.
So for like this is a lot of
Yeah. I mean, basically the same, right? You go from O to O prime,
yeah.
some distance, and then you don't have the rest of that.
I think it's the fact that it's like O prime, I think it's like the designation for it.
O prime,
What would you call it? I don't know what to do.
that one's like a moving frame.
Okay, whereas O is stationary, right?
Yeah, O is like on the ground, can't go anywhere, so O prime. Yeah,
It's just like where it's where
so like,
Yeah, it's a spring attached to a point that's moving. Yes. So O is not moving.
it is not,
And O prime is where the spring is, right?
but yeah, O prime is
Gotcha.
no, not one. It is kind of weird. But it does, this would be like steam problem. You're trying to Earth and the moon. You know, like going around the Earth, going around the sun. So your fixed origin is now the sun, and the O prime is the Earth. That is pretty neat. Okay. Hold position, you know, it's constant velocity. Hold position. Oh, okay. Yeah. That was really nice.
Yeah, for the A, we just do the Y position. Y position, yeah, it's and do like X.
I think it's ass.
Like on
Just before I get through here.
well, yeah. X distance is just
Yeah, I don't know how many different short ones X and Y.
Yeah.
Or you make like a big.
Yeah, I think. And then you would find the Y position.
then we would need another equal that's a function of data. Here we have policy. So we give it data.
Yeah, we even like we even wrote both of that.
Yeah.
I'm impressed most people jumped right into velocity. Usually that's where I have more trouble, but more people were like, oh, velocity is going to be a VO plus that VP/O. And I'm going to leave that blank for a second. Did anyone else have something like this? Okay. What's missing in that underlined part? What should I put there? Where is that VO pointing?
Cosine theta B1.
Cosine theta B1, something.
I think it's E1.
Like an E1? Yeah, because this one, sorry, we should write the units, right? Or unit vectors. Was there another suggestion along E1? Is there any difference between E1 and B1? They're both unit 1, right? Magnitude 1, and they're both pointing in the same direction. So it's the same thing, whether you want to call it E1 or B1. And to leave it like this is totally fine. You can say, this is it. I need one unit vector of V0 along B1, and then I need this other kind of cylindrical coordinate system. They're not orthogonal, right? Like B1 is rarely orthogonal to ER or E theta, but it's okay to mix and match unit vectors as long as you don't like take a cross product and set it to 0. Like, I don't need to do the math there. We can do cross product, like, or dot products, right? Like dots and crosses. We just need to remember. Yeah, and that's it. That's all we needed. Does that help us with P, with the position? Position of P? If we're moving 10 meters per second, how far did we go in 1 second?
10 meters. So
10 meters.
In other words, the velocity time for time is
Yep.
plus the initial length of our current.
Yep.
Okay.
Because really what that's measuring is this distance. V0t. And we could call it V0t plus whatever initial position it was, but I don't know.
We're assuming a 0. So it's assuming O and O prime are the same, T equals 0. So no.
Yeah. And then add this vector that we already V0t and that B1 plus that RER. Cool. and that one's B, right? I'm trying to stick to all right, we started off with a lot of times the first thing we do is draw a free body diagram. Things get harder quicker, so it makes sense to define like what is position and velocity before you jump into that. And that's why this process is like, what are the kinematics? How are things moving? Now, what are the forces involved? Like, how is this thing? What's going on here? And it says there's no gravity, but at least the way I think about it is like gravity is just normal to the picture, right? Like acting into the page rather than pulling it down. It doesn't you're not asked for kinetic diagram, but I want you to try drawing that anyway. See what you think. Because we looked at velocity, so what is that change? What is the change in velocity here?
Frame constantly, the velocity of the spring should be changing.
Okay, yeah. Yeah, so we could say that. Spring main thing changes velocity.
Like I think your intuition is right. Like if it's not moving and you give it a velocity, then yeah, it's having some impulse supply. But during steady state functions, right now it's speed. Should have like I guess dB 0, dt 0, so yeah. And MA from that moving range. Okay. Yeah.
I thought it was being accelerated to this. Like, oh, it was being accelerated to.
Yeah. Yeah, now one kind of conception. This, it's We're not really solving for motion, but it looks like, you know, it's stretching, more stretches, slower moves. As the arm gets small, it spins faster. Wide radius, small, move very fast.
Here, I'll draw. Just to give us like a frame. Did I miss anything? No gravity, yeah. At least not in B1 and B2. There is no component of gravity along B1 or B2, or E1 and E2. It seems right? It feels too easy. I guess that's part of, like, I saw people like trying to scribble in extra stuff, but that's all we need. Yeah.
Why is there no gravity?
Gravity is acting like along that B3 direction. So perpendicular to our plane of motion. Why is that? Or, yeah. So the way that I like think about this problem is like, if we had like if you had a big extended ball, we saw like for a linear pendulum, for the simple linear pendulum, it looks like a spring. There's like a G over L times theta value. And that's kind of what we have here of like, if we change the angle in any direction, it's going to swing back to where it was. So now we take that whole table, like a wrecking ball sort of thing, and we start driving it along. The whole thing is going to, initially it'll start swinging back and forth, but really if there's any vertical movement, it's going to swing around in a circle. And not really a circle, it's like an ellipse, because as it gets closer to the center, it moves faster, and then as it gets further out from the center, it moves slower, so then it wants to get pulled back in. So we end up with this like elliptical orbit around our two angles of 0. That's kind of the way that I think about this problem.
So like the frame of reference is like looking down on that.
Yeah, so our frame of reference is describing like what is this R and what is that theta downwards. Yeah. So there is gravity, but it's not the thing pulling it back to 0. Or you could say there's no gravity, and I guess it would be the same thing. What did the kinetic diagram look like? What's our mass times acceleration? Because that's what is our change in momentum? Our mass times acceleration. There could be like a change in radius. What would lead to that? Like, what's the parts of that?
I think there would be one along the same way as the spring force.
Radially, so like an MA. So Jimmy says MA theta. Okay. Oh, do you think it's always like centripetal acceleration? That would be true if the stiffness of the spring was so high that the stretching was negligible, right? So now it's just swinging around on a string in a circle. But here, if the spring can stretch and relax, then there's got to be like two components. So again, we're just trying. We don't need to know everything. We just need to get it in terms of like a couple of things that we are trying to solve for. So in this case, like r and theta. So I could call it my MAR and my MA theta. And that would be acceleration in that O prime, in that moving reference frame. Do I need to add acceleration from the fact that it's moving? Why not? Constant velocity, yeah. So sometimes you don't have a constant velocity like moving reference frame. Yeah, the constant velocity, and that means, so constant velocity frames are called inertial frames. So F equals ma, you can use either the constant velocity or you can use a fixed reference frame. It doesn't matter. So this is our inertial reference frame. Technically on Earth, we call the Earth an inertial reference frame. Like all the time we say like, oh, it's kinematic motion. F equals ma, ng equals ma, so a equals g, but really we're on a rotating reference frame. Like the Earth is changing. Like every day we go through a full 360 degree rotation. So we do have roughly. Why roughly? Isn't that our definition for time? Isn't it basically rotation? Or a sense? Yeah, I guess. I mean, we do have like a full year is 364 and 3/4, like a quarter. Is that right? And every 4 years we have the leap year. Time is complicated. Time is weird. Yeah. But we're spinning. There's always centripetal acceleration. So there are things called the Coriolis and the Otvos effect. They're very small, so most of the time we just say like, it's fine. It's an inertial frame. But inertial reference frames are technically constant velocity. There's no acceleration. Yeah. Yeah. If you're on the northern versus southern hemisphere, the toilets spin in a different direction. There's a great Simpsons episode that we just rewatched recently where Bart goes to Australia to try to prove that toilets spin the same way, but Lisa was right. And sure enough, they spin the opposite way. At the equator? It should go straight down, but you're never exactly on the equator, and so it goes one way or the other. Cool. Thanks a lot. We'll pick up next time.